Thank you for the introduction. Hello, everyone. I'm Sirui Ning, a second-year postdoc at UC Berkeley. So first of all, I would like to thank Jing and other organizers for inviting me to speak at BPPB. So today, I will talking about our recent work on the thickness effects in the electromechanical stability of biological membranes. This work was done with my supervisors, Kranti Manadapu and Karthik Shekhar, and in collaboration with Dr. Yannick Omar at MIT. Okay. So, biological membranes play essential roles in living systems. They are not only interfaces for electrical signaling, but also dynamical systems that exhibit mechanical responses and electromechanical coupling. So, you can see this video is a modern measurement of action potential using the voltage sensor from Adam Cohen's group in Harvard. You can see clearly that there's a wave of transmembrane potential change, showing that the propagation of the electrical activity in a neuron on an extremely short time scale, which is milliseconds. And the second is that mechanical responses. So a biological membrane is a two-dimensional fluid in plane, but behaves like an elastic shear out of plane. So this video shows the mechanical responses of a neuronal cell. The circle is an optical tweezer, and what they are going to do is to take the tweezer and torque up a piece of membrane and forms a tube, which is already a non-trivial shape. But now, as they move this tweezer around, you will see that the liquids are quickly flowing and dynamically readjusted in plane to accommodate this large out-of-plane shape changes. This kind of behavior is only possible when the membrane is in-plane fluid and out-of-plane elastic. And third, the video shows that the electromechanical responses of a vesicle on the applied voltage. You can see that when a voltage is turned on, the vesicle changes shape and becomes elongated along the direction. And after the voltage is turned off, the membrane gradually returns to its original shape. Then, one key question we want to address is that what determines the electromechanical stability of biological membrane? So as a first step, we study the following problem. When a flat biological membrane is suspended in an electrolyte solution, how do surface charge and applied voltage affect its stability? You can see that this picture shows a model system. A membrane separates the two electrolyte regimes, and a voltage is applied across the system. The two sides of the membrane may carry different surface charges, which characterize using two parameters, the average surface charge and the surface charge asymmetry. We also have a membrane thickness. Then these are our problem setup. Then on the right is a response we want to focus on, namely the membrane height fluctuations. We decompose the membrane deformation into modes with different wave numbers, and then analysis whether this fluctuation decay or grow with time. In other words, the main purpose of this slide is to set up the problem. Under different conditions of voltage, average surface charge, and surface charge asymmetry, does the membrane remain stable or does it become unstable? So this is actually an old problem and has been considered by many biophysicists. There are three main approaches. The first is a free energy-based approach using the average free energy. This framework is an equivalent description, but our problem is actually non-equivalent. The second is a finite thickness static approach, where the membrane is treated as a dielectric slab with a finite thickness. This captures the internal membrane structure and more realistically, but most studies in this category are restricted to quasi-static situations. And finally, is a zero-thickness electrokinetic approach, typically based on Poisson's Planck type dynamics. This framework can describe ion transport and coupled electrohydrodynamics, but it usually simplifies the membrane into a zero-thickness interfaces and therefore loses the finite thickness structure. So there's a gap. The existing series treat the membrane too effectively. For example, they treat the membrane as a zero thickness and they do not resolve the voltage drop across the membrane thickness or the stresses acting separately on the two surfaces. So the full electromechanical coupling is still missing. So our work seeks to consider this problem more systematically. Then, so here I'm starting from the governing equations. So first we introduce the governing equation, the bulk. For electrokinetics, you can see that the Poisson, the first is the Poisson-Planck equations describe ion transport in the bulk. The concentrations of each ion species evolves accordingly to the divergence of its flux. And this flux includes both diffusion driven by the concentration gradients and the electron migrations driven by the electrical field. And then the electrostatic potential is determined from the local free charge density through the Poisson's equation. And then for the hydrodynamics, the electrolyte flow is modeled as an incompressible flow. So the velocity field satisfies a divergence-free condition. And then the fluid also satisfies the momentum balance equation under Lorentz forces and is modeled as a Stokes flow. So the inertial term is approximately zero. Then, after writing the bulk equations, we now need equations for the membrane itself, deriving from the 2 plus delta theory. So this theory is established by my supervisor, Kranti Mandadapu, and his student, Yannick Omar. So I would like to introduce the philosophy first. So I want to stress that 2 plus delta theory is not to patch specific missing terms in the existing theory, but it is to build a general continuum mechanics framework first, where the balance laws are derived independently of any particular constitutive model through dimensional reduction. So for details, I refer you to the these original three papers. Uh, so here I just briefly introduce the governing equation for the membrane. So these equations describe mass balance, in-plane momentum balance, and out-of-plane momentum balance, or the shape equation. So since the membrane is deformable, these equations are written in the differential geometry language. So for the momentum balance, it relates the in-plane surface velocity to the normal motion of the membrane. Intuitively, if I pull or bend a patch of membrane so that it moves in the normal direction, it would create a local area change. Then the in-plane flow has to come in and fill that gap so that mass is conserved on the membrane surfaces. Then that is the physical meaning of the equation. Then the in-plane momentum balance describes the tangential stresses within the membrane. It includes contributions from the membrane tension, bending elasticity, surface viscous stress, and tangential tractions from surrounding electrolytes. The purple term uh, captures the corrections arising from the 2 plus delta theory. And finally, the out of balance equation, also known as the shape equation, determines how the membrane deforms normally under this geometric effects and its bending rigidity and the surface stress tensor. So the purple term again arising from 2 plus delta theory, and it's a new term due to the finite thickness effect. Okay, then in order to understand the instability of height fluctuation, we need to understand its growth rate. So you can see that the growth rate comes from this dispersion relation in the plane wave decomposition. This Q is a wave number, and this mu is a bulk fluid viscosity, and this lambda effective is the effective tension, and this Kb effective is the effective bending rigidity. So the stability is basically controlled by the effective tension actually in the long wavelength limit where the Q is small. So you can see negative growth rate means positive effective tension and means stable, and positive growth rate means that negative effective tension and therefore means unstable. So physically, zero effective tension marks the boundary between you stretch the membrane and compression the membrane. A positive effective tension stretches and then stabilizes the membrane, while a negative effective tension means that the membrane is being compressed. So the nature of this instability is very intuitive. It's like squeezing a thin sheet by hand. Once the compression is strong enough, small perturbation grow and the membrane buckles, and it can eventually break down. The important thing is that the tension and the bending modulus are both effectively modified by electrostatics, so not only by the applied voltage, but also by the surface charge and their cross term. So the rest of the story is really about figuring out how these parameters modify effective tension and bending rigidity. To answer this question, we need to understand each term's contribution. So we start from the bar plot first. The difference uh, between these two cases, case 1 and case 2, is a screening strength. Case 1 corresponds to strong screening, which means that the thickness of the membrane is larger than the debalance. And while case 2 corresponds to the weakly screening case, which means that the thickness of the membrane is smaller than the debalance. On the left, you can see that the wattage contribution is always negative, always negative. So it always dissipates the membrane. The surface charge, however, depends strongly on the screening strength. On the strong screening, it is stabilizing and it contributes positively to the effective tension. But on the weak screening case, it contributes negatively to the effective tension, therefore dissipates the membrane. Uh, then for the bending rigidity, you can see that for all voltage or the surface charge, it all contributes positively to the effective bending rigidity. Therefore, the bending is always stiffened on the electrostatic static interaction. So the main result here is that screening mainly controls stability through the effective tension. Now, after understand this, we can move one step forward and ask how voltage and surface charge influence the dispersion relation, and under which regime the membrane is stable or unstable. So this slide answers this question and give the dispersion relation and the phase diagram. I think this is a key result of this talk. So for the strong screening case, you can see that so this red line is just the bare membrane, and you can see the frequency is negative and it's stable. And then applied voltage dissipate the membrane, and you can see that the frequency become positive. However, adding surface charge where can stabilize the membrane and make the frequency negative again. So this is also reflected in the phase diagram. So where we denote the unstable regime by red color, and the blue and the stable regime by the blue color. So for the fixed applied voltage, you can see that when you increase the surface charge, the system would move from the unstable regime to the stable regime. And however, for the fixed surface charge, when you increase the applied voltage, the system will move from stable regime to the unstable regime. So this phase diagram tells us that how to control the membrane stability experimentally. And similarly, for the weak screening case, applied voltage still dissipates the membrane. However, adding surface charge in this case would largely dissipate the membrane. In the phase diagram, you can see that increased surface charge density would decrease the stability regime. And moreover, you can see from this phase diagram here that under weakly screening, the membrane stability becomes much more fragile and can be disrupted more easily. Then then a natural question is how does our theory correspond to the experiment prediction? So this slide shows that including final thickness factor will move the predicted breakdown voltage significantly closer to the experiment. So in experiments, the membrane breakdown voltage corresponds to the onset of electroporation. As the applied voltage increases, the membrane initially deforms in a mostly reversible way. Once the transmembrane potential reaches to a critical value, however, pores begin to nucleate, and then the membrane conductance rises sharply, and leakage or rupture can be observed. Therefore, the measured breakdown voltage provides an experimentally threshold for the instability of the membrane. So across these four different lipid systems, you can see that our theory reduces the discrepancy compared with the previous theory. So then we want to ask, where does this improvement actually come from? If we revisited the membrane shape equation, the key contribution is not the Euler term 2, but term 1, which is new in our 2 plus delta theory. The term is specific to the finite thickness distribution, and term 2 is the old term and essentially recovers all the previous result. Then the question is, what is term 1? How do we understand term 1? So before we answer this question, I just want to show you a few more examples of effective tension in different conditions. This slide compare our effective tension with the existing series into limiting cases. In the first example, we set applied voltage to be 0. We only have surface charge. If we keep only term 2, then we exactly recover the classical surface charge result of Winterhalter and Helfrich. But the full theory, you can see here, contains an additional thickness dependent, which arises from the term 1. So the surface charge correction to effective tension no longer always lower the tension. Instead, it may change sign when the thickness of the membrane equals to the debalance. In the second example, we set the surface charge density of the membrane to be 0. So recent zero thickness electrokinetic series again recovers only our term 2. The full result actually, due to the term 1 new contribution, it is different, and it's not a small contributions under physiological screening case. So then for the completeness, I'll show you a table which decomposes the electrostatic corrections to the effective surface tension into 3 physical sources: surface charge only, applied voltage only, and cross voltage charge contribution. So the first column summarizes what the previous theory predict. The important observation is that these previous results are exactly recovered by our term 2. The new part is the term 1, and shown in the last column. This term comes from the finite membrane thickness, or more precisely from the traction moment across the membrane. So you can see that for the charge-only contribution, this is important. Term 2 is negative, but term 1 is positive. So which means that there's a competition between the membrane thickness and the debalance. For the voltage-only term, both contributions generally reduces the effective tension. So voltage still tends to destabilize the membrane. And the mixed term, you can see that it depends on the charge asymmetry between the two leaflets. So it can either enhance or oppose to the voltage effect depending on the sign of the leaflet asymmetry. Okay, so now in this slide, we explain the physical meaning of term 1. So it is a thickness traction moment, which only appears when we keep the membrane as a finite thickness object. You can see that Q alpha can be viewed as a total shear force across the membrane. Then we want to ask what is the relative contribution of term 1 and term 2 to effective tension and bending rigidity. So again, we're using the bar plot to visualize this. This slide shows that under psychological screening, the term 1 is not just a correction. You can see that it actually dominates dominates the electrostatic renormalization. On the left, for the effective tension, on the right, for the effective bending rigidity. We compare the relative weight of term one and term two. So what you can see is that in the most cases, especially on the strong straining cases, term one contributes to the majority of the total electrostatic effect. So this tells us that the final thickness contribution is not a small refinement. It is the leading mechanism setting both the effective tension and effective bending rigidity. In other words, under psychological relevant conditions, you cannot really ignore the membrane thickness if you want the correct electromechanical stability. This is a takeaway message I want to send in this talk. So, and then in this slide, I want to provide another explanation of term one in the virtual work method, which is a more mathematical way. So to understand where the term one comes from, we look at the virtual work done by the electrostatic attractions on the two membrane surfaces. So the upper and the lower membrane surfaces are located at x plus and x minus. So this x0 is a position vector for the midplane, and n is a surface normal vector of the membrane, and delta is a thickness of the membrane. So now assume that the midplane is deformed along the normal direction by a height of h theta. Note that the normal vector would also change under these cases. Using the Wingerton formula, you can see that the variation of the normal vector is proportional to the in-plane gradient of the height field. So therefore, the virtual displacement of the upper and the lower surface has two pieces. The first piece is along the normal direction, which moves both the surface, upper and lower surface together in the normal direction. When the electrostatic attractions do work on this virtual displacement, we do get our term two in the previous series. What's new is the second piece coming from the fact that there's a finite thickness between the two membrane surfaces. So which means that when the normal rotates, the upper and the lower surface move tangentially in the opposite direction through integrated by part. This you can see that this becomes term one. Okay, so finally, I want to summarize and acknowledgements. So I want to thank my supervisor, Professor Kranti Manadav and Professor Kasik Shekhar, and my collaborator, Dr. Yannick Omar, and my colleague, Josh and Jafar. So the conclusion for this talk is that under physiological condition, surface charge is stable as a membrane, and it might providing a potential explanation of why charged membrane can exist stably in the nature. Okay, so that's all for my talk, and thank you very much for your listening.
Well, let's thank Sirui for the wonderful talk. So please put your questions in the chat. Sirui, maybe I can start with a question. So I think you have this table comparing your theory and the previous theory and how much how much the error is. And so there's still some kind of remaining sort of deviation from the experimental data. So how would you sort of envision that would be additional factors to be, that hasn't yet been taken into consideration or hasn't been modeled accurately?
Yeah, thank you for your question. This is a very good question. So note that the setup for our problem is that we are still under the linearized regime. So we haven't captured the nonlinear effect in our theory. So but in the experiment, when the membrane actually break down, it may rupture drastically, and therefore some nonlinear effect might contribute. which may not be easily captured by the linearized theory. That's my current understanding.
Cool, cool. So maybe a question a little bit related to what Professor Stockerweg was talking about. So how would you uh, envision that, maybe having proteins, transmembrane proteins in the membrane structure, how would that, affect the stability and these electromechanical uh, system and the dynamics and equilibrium.
Yeah, this is a great question, and actually, this is our current one of the things we are considering. So, when you act adding the proteins into the membrane, there will be a lot of new effects. For example, if the protein is like an ion channel, then you may open the when the ion channel opens, it may produce some extra Maxwell field, and this will contribute to the membrane balance equation as well. And this is so how to consider this problem depend on how do you model this protein in the problem. By model, I mean that how does this protein would produce any uh, Maxwell electric field?
Okay. Maybe I have a third question since nobody has put a question in the chat yet. Uh, So, like, as far as I understand, so you were doing basically something similar to a linear instability analysis to your equations, right?
Yeah.
So I'm just wondering, like, did you also perform any sort of simulations of the dynamics, and does it kind of resemble what's been observed in the experiment?
Oh yeah, so because the difficulty, yeah, this is an important question. So the difficulty to simulate this problem is that because the membrane is deforming, so that means that when you do the simulation, it means that the boundary for your partial differential equation is moving. And our group, I remember my collaborator Yannick Omar and Amesh Sahu, and in my group, and my supervisor Kranti Madadav has developed a finite element method specifically using to simulate this kind of problem when the membrane's boundary can change with time. Yeah, this might will definitely be studied in the future.
I see. So what about, like simulating on a small vesicle system? And so you can basically apply some constraint on the total area of the membrane. I mean, would that make the simulation more feasible?
Yeah, this is a very good point. I actually haven't think about it before. I need to think it more carefully.
Okay. Let's thanks Saray again.